Today we are going to start a new topic, that is availability. In my last videos I told you about reliability. Now here this is another topic, that is availability. So what availability basically is, it's just a little difference in this. It is the probability of an item to work at certain time, that can be t, considering the maintenance operations. So there is just the chance of maintaining or of repairing our item. So that is the availability. So what is the availability? So how much is the availability of an item to get repaired? So in this we have MTTR. What is MTTR? MTTR is the mean time to repair or the mean time to restoration. So in the reliability we have MTTF or the MTBF, mean time to failure or mean time between failure. But now in availability we have MTTR, that is mean time to repair or mean time to restoration. So here we have lambda. We know that lambda is equals to 1 over MTBF, where MTBF equals to 1 over lambda, and the new thing that is adding, we have mu, that has a formula of 1 over MTTR. So here we have mu, and what is this mu? This mu is the repair rate. Okay, so it's mentioned here, lambda is the failure rate and mu is the repair rate. They both are constant for an electronic component. So mu is the 1 over MTTR, and MTTR is measured in hours. So as you know that we have a failure rate, and it is the unit for failure rate is failures over hours. So here where we have mu, that has the failure rate of 1 over hours. So 1 over MTTR is equals to hours. So how we can give the equation or the formula for the MTTR? If you remember, if you know that for MTTF we have an equation that is going from 0 to infinity, r of tau and d tau. That was for MTTF, but now we have MTTR, which has the equation of from integration of 0 to infinity, the limit going from 0 to infinity, x f of r, tau and d tau. What is this x? X is a random variable, it can be anything. And what is this f of r? It is the probability. For f we have PDF. For f is represented as the PDF, probability density function. So f is the probability of repair, tau times d tau. So, and we have another thing, availability. So what is this availability here? Availability, this a times infinity means that the time is at infinity. A is represented as steady state availability. Okay, when we have the limit of time is infinity, when we have time at infinity, that is called steady state availability. And it also has another formula. I mean, it also has a formula, that is A infinity is equals to MTBF over MTBF plus MTTR. So mean time between failure divided by mean time between failure plus the mean time to repair. Okay, this thing is for availability. Now we have a kind of, a method, or you can say a complete chain to provide to solve this A infinity, like how we can describe it. And we have a complete kind of procedure to represent all of this, to represent availability and everything, and mean time to repair and steady state availability. All these are represented in a kind of big kind of procedure that is called the Markov memoryless diagrams. It is inhomogeneous. It is inhomogeneous and it is a Markov memoryless diagrams. It's a kind of chain. So what's in this? How we can solve or how we can represent this kind of procedure, how we can do it, or the method for doing or for drawing this chain or the diagram for this procedure. I'm going to explain you now. Okay, so first we have to keep in mind five things. That is, we have a lambda, that is the failure rate, number one. Number two is our mu, that is the repair rate. They both are constant for an electronic component. The third we have to keep in mind, third thing is delta t. What is delta t? Delta t is our time step. Okay, and we have this gamma delta t, that is a transition state. And remember that the all states are a finite number. States are a finite number, means they are in numbers that are finite. Okay, so these five things we have to keep in mind, and our Markov chain will be only based on these five things, will be regulating and revolving around these five things, in which lambda and mu are very important. Well, what we have now, lambda is our failure rate, mu is our repair rate. So how we can solve this, how we can make this kind of chain, and how we can provide this table, uh, how we can solve this table, not solve, I mean how we can keep the values of this table by giving, suppose we have an RBD, we have just an RBD like this. We have an RBD, that is, here is the start point and here is the end point. This is an RBD. So RBD is the reliability block diagram. So this is our suppose this is our element. We have one component only in this RBD. We have only one component, that is that can be anything. Suppose we have a component here. Okay, we name this as A. So how we can represent the scenario, how we can represent this component uh, through this Markov chain. So let's see next what is, how we can represent this chain. So we have two states. Obviously when we have a component, we have its two states. One is the working state and the another is the failed state. Obviously any component, suppose this component A, it's gonna work when it's in the starting position. It's in the working condition, and as time passes, so it will be going to the failed condition. Okay, so how we can represent the table? This is our W of t, that is the working condition at time t, and failed condition at time t. And what is above, we will write here W t plus delta t and F t plus delta t. So this is our working condition at time t, and there will be as the time will pass, there will be some changes in the time, there will be some changes in the condition of our item. So that is represented by step our t will be changed. So this is represented as t plus delta t, and here the our failed condition of the item is also represented by t plus delta t, because obviously we have an item that would get failed, so there would be some procedures to repair it, because we are talking about availability. So we also have to see that the item that is going to fail, that is failing or has failed, so we have to repair that item and make it towards the working condition, bring it towards the working condition. So obviously at time t, when it is failed, it would be added to plus delta t, that is the time step, and it would be added because it's going to step by step to the working condition, from working to failed condition and from failed to working condition. So here, that's why I hope you can see it clearly. We have given this arrow that is showing that W is going from work condition to the failed condition, and when we are going to repair the item, because it's availability and we have to repair the item, we repair it, so it's going from failed condition to the working condition. Okay, and how we can put these values, these four terms, how we keep them. So it's necessary to see, this is the main thing to understand. When we were in the working condition and start, I mean to say at t0, when we were in the time at t0 in the working condition here, so we keep as 1 minus lambda delta t. Why we do it like this? Because lambda, you know, the failure rate. So in at working condition we have just the item as mu, so there would be no failure rate, there would be no failure, so that's why we keep it as 1 minus lambda delta t, no failure rate. Okay, then we move from working condition to the failed condition. So when we came here, what we see, we have lambda delta t. Why is it so? Because from working condition to the failed condition, now the item has got failed, it is failed. So when it is failed, we have a failure rate obviously, so the failure rate is lambda delta t. So it's when we were in the working condition, and it's when the item has got completely failed. Now we have talked about the working condition and the working to failure condition. Now we would be going towards the repairing condition, that okay, we have known that the item has failed. Now we have to apply we have to apply the repairing conditions, repairing scenarios, and we have to repair the item. So when we were at working, and here we have at the failed condition, so what we will do, we have mu delta t. Why is that so? Suppose we are going from failed condition to the working condition. Obviously here is w and here is f, so we are going, they both are here. Above we can see that we have to find the w of t plus delta t, and we have to find this f of t at the failed condition. So this means that we are going from failed condition to the working condition, and we are on the process of repairing of our item. So when we were here, we go from here to here, so we keep it as mu delta t. Why we bring it here mu delta t? Because our system, our item is going to repaired now, so mu is the repair rate and delta t. So that's why it's the same. You can see that it's when we were over here, and it's now we are here when we were going from working condition to failed condition. At working condition, the item, there was no failure rate, so 1 minus lambda, and at here at failed condition, our item had got failed, so we were at completely failure rate. We were at completely failure condition. But when we go from failure to working condition, we come here. So first we are going to repair our item. We were repairing our item, so by going to repair, it was mu delta t. This is the mu is the repair rate, and also when we were not repairing our item, we were both in the failed condition, so we keep it as 1 minus mu delta t, as the item has not started to get repaired, it is unrepairing. So now how we can, so it's a really easy one. As you can see that we have only one component, that is the one component, that is either not series, not parallel, or only one item we are working on. So it's a really easy chain for this one, and a really easy table. This is a really easy one, but as to start the topic, I have to explain with the initial conditions, obviously. Okay, so how can we keep these equations into our, I mean these are not equations, sorry, how can we keep these four things into the form of equations? So first we have to keep them in the form of probabilities. So how we can define our probabilities? Our probabilities would be the probability of the working condition at time t plus delta t. So we are talking about this. probability of working condition at time t plus delta t would be every in this equation would be all the things related to here, that would be in the wt plus delta t. So we'll talk about these things, okay, when we are in the working condition. So 1 minus lambda delta t, and where it is, it's the probability of the working condition, it's in wt. So probability of wt plus the another one mu delta t, and where it is here, probability of the failed condition f of t. So f of t, got it? When we were in the first part, probability of working condition, we keep these two things in multiplication of this and this with their probabilities, and now we named this equation as equation 1. And now when we are in the probability of the failed condition from time t plus delta t, you can see that what we did, we bring lambda delta t, and where we were in the working condition, so we wrote it as probability of wt plus 1 minus mu delta t, and probability of f of t. Okay, so we named it as equation 2. That's really a lengthy one, but it's a really lengthy topic as for explaining all the things and to end it from zero to end the topic. It's really important to know all these steps, and we have to go step by step. So we named it, so come towards the equations, we named it as equation 1 and equation 2. Now what we did the next step, first we see that this is multiplying, so we do the simple multiplications. We wrote it like this. We are working on equation 1, pw of t minus lambda delta t pw of t plus mu delta t pf of t. Okay, so first we are taking the equation 1, we are working on equation 1. So we got this thing like this, and we see that pwt it's here, so we have to bring it out to the other side of the equation. So we brought it here, pw of t, it comes here, so it's in minus, equals to minus lambda delta t, pw of t remains here as it is, and it's here, mu delta t pf of t remains here as it is. Okay, and now notice the next step, we see that delta t and delta t, they both are common here, they both are common over, so we'll take this delta t out, and this delta t will go in the at the other side of the equation, and in division, here it is multiplying, so here it will be gone and would be division, would be in division. So this is remains the same, it comes in division, and this thing comes the same way, and we name it as equation 3, because now we have to work on equation 2. We have to do the same procedure as we did for equation 3, same to the equation 2. We have to do it same for equation 2. Okay, now what we are gonna do now, you can see that we take the p of f. Okay, pf t plus delta t equals to lambda delta t pw of t plus now this pf of t will multiply with this one, and this would multiply with this, it got like this. Okay, and the same that we did before, pf comes here, and we have left on the right hand side this thing and this thing, then we again bring the delta t outside as common, and it will go here on the left hand side and in division, and this are in the form of this, and the same we named it as equation 4. The above one was 3, now it's 4. Okay, I hope everything is clear till now. Now we will be doing the derivation of 3 and 4. So here it is equation 3 and here it is equation 4. We have to derivate them. By derivating these equations, this delta t will be finished it out. Okay, so by doing our derivation, you know what derivation is and you know how to do it. So pw of t equals to minus lambda pw of t minus mu pf of t, and the same for pf of t. Oh, sorry. Here is equation 3. We do the pw dot t for this equation and pf dot t for this equation. So what it brings out equals to lambda pw of t minus mu pf of t, and the above one was, you can see that, minus lambda pw of t plus mu pf of t. So these are the both equations that we got. Now what is our main part? You can see that we have our functions are in time and we have to bring them in the s domain. So they are all in time domain and our focus is on to bring them in the s domain. So how we will be bringing them in the s domain? There is a simple method of doing this. It's the Laplace transform. You must be knowing it. So after putting the Laplace transform on this thing, like we have you must be knowing that how the Laplace transform is done. So we do the Laplace transform of the derivative of x of s. So we got as x of s minus x of 0. Okay, and what's next? And when we do the Laplace of simple x of s, so it's s of x. For derivative thing, you have a Laplace of like this, and for the part which is not a derivative one, you have a Laplace of this. So we have both the derivative ones, so we only focus for this one. So Laplace of this and this and this. So as we keep this x dot s to w dot t, what we got now? We have s here, x of s, our x of s is p of w. Okay, okay, it's p of w minus x of 0, x of 0 1. Oh, why we keep 1 here? Because you can see that we are taking some initial conditions here at initial conditions at time 0. So when we are talking about initial conditions, what would be the initial conditions? Obviously, when we are in the initial conditions means that when we are at time 0, so obviously our probability of working condition would be 1, because our item would be untouched and it would be new, so its probability of working would be 1, would be very good, and it's 1. And what would be the probability of failed condition? Obviously at initial conditions, when we are talking about the probability of failure, so it would be 0 because the item is new, so it can't be failed, so it's 0. And you know that probability is given between bounded between 0 and 1. The reliability of an item is bounded between 0 and 1, so we would be only talking about 0 and 1. So that's why we have keep 1 here. Now you got it. Where it is? Yeah, here it is. Okay, so what was that? As probability of pw minus x of 0, when the x of 0 is when we have p of w at 0. Okay, we are taking x of s as pw. Okay, so we have pw at time 0. So when it is at time 0, we have given before pw of 0 is 1. So that's why we have keep 1 here, equals to other things remains the same, they came here, and we are going from time domain to the s domain, so that's why this time is neglected, it would be removed. Okay, and we named it as equation 5. Now the same procedure we did for our pf of t. So here it is, pf of t. Now we have s and pf, like as before we wrote pw when we were in the we were doing for pw of t. Now for pf of t we will be pf, and what's next? It's minus x of 0. So when we have the probability x is pf of 0, so what we say that the probability of failure when we are in the initial conditions at time 0 is 0 because our item is new and it won't be failed, it is completely new, so no failing conditions, so it's 0. So that's why we keep 0 here. So x of 0 is 0 and rest things lambda pw and minus mu p of f remains the same. Okay, it remains the same and this 0 is neglected and this thing comes here, this thing comes here, this thing comes here, and we name it as equation 6. Got it? The upper one was 5 and now we have a 6 equation. Okay, now what is our purpose to do? Now we have to bring our pw, we have to bring the values for pw. So you can see that in equation 5 and equation 6 we have pf and pf. This pf is irritating us. We have to remove this pf and we want only pw. So how we are going to do this? We have to, first of all, we have to bring this pf value, okay, and we have to bring the value of pw and keep it at equation 5 here, pf. So how we are going to do this? We took this equation, this thing comes here and equals to this. We are in the procedure, we want to create a value, we want to find out a value of pf, an equation of pf, okay, so that we can keep it at equation 5 in the place of pf, so that we get all the terms related to pw and there would be no pf, so this pf won't be disturbing us. Okay, let's come towards this. So you got it, we bring it here and lambda pw. So pf and pf is common here, so we bring it as common. S plus mu equals to this remains same and pf equals to this and this thing comes here down. So we got a value for pf, we have a equation. Okay, this is its value and we named it as equation 7. Now what we are going to do now, we have to put this equation 7 in 5. I told you that this pf is irritating us, so we want all the values of pw, so we keep the equation now in we keep this equation, the value for pf in equation 5. So so you can see that there would be all the things related to pw, so we have got it pw. Now what we are going to do, here it is, we have spw minus 1 same, okay, lambda w mu and pf in replacement of pf, the value for pw. Okay, this is simple multiplication and division, simple mathematics, nothing so much irritating or difficult. So what's next? What we are going to do now, first of all, we bring this one that was a separate one, we bring it here, so it minus becomes plus, and this thing here, see, this thing and this thing, we bring it here and this one here, so that this pw, all pw's comes together. Okay, so pw, lambda pw and lambda mu pw s plus mu, sorry, it comes here and signs changes, so the pw is common in all three, so pw comes out and s plus lambda minus lambda mu s plus mu equals to 1, so it comes in common and pw equals to, sorry, not equals to, now first we have to do this LCM thing and we have to bring s plus mu all over the other part also, so we multiply this s plus mu with the whole term, with this term, so s plus lambda, s plus mu multiplication minus this remains same as it was already in denominator here, and s plus mu remains same equals to 1. So that's only the subtraction, that's only the multiplication mathematics and nothing else. And how it becomes, this thing multiplies, when s is gonna multiply with this, it would be s square, s is gonna multiply with lambda, so s lambda, this mu would gonna be multiplied by s, so s mu plus mu lambda. So the same thing is here, and this minus mu lambda comes here, and this thing s plus mu, it's remain here. So what we get now, we got two terms that are identical with different signs, so we can cut them off. Equals to 1 is always here, and so this is the thing that we got. Now we can see that we have s plus mu, so it would go there. Simply we have to find out the value for pw. That would be, we can easily find it out. So s square plus s lambda plus s mu, it comes here, and s is common in all three, so s would come out, and this will like this, and this would be like this. So pw equals to, this remains here, and this thing that was in multiplication goes in division. So when it goes in division, s times s plus lambda plus mu, bracket close. Okay, so now we have find out the value for pw. Now what we are going to do, obviously we have taken our equation in s Laplace, in s domain. Okay, now our task is to bring it in again in the t domain, time domain. So again we have to apply the Laplace inverse, obviously. So by applying Laplace inverse to this thing, you know that how we can apply Laplace inverse to this thing. We have the method for a over s plus a over a plus b, and this would gonna be a, this is gonna be b over, you know that Laplace and inverse, you must be knowing it, a over s plus b over s, that how we solve these things. And you also know, or you can google it out, or you can learn it by heart, obviously, that the inverse of Laplace a over s, inverse of a over s, Laplace inverse of a over s is u over u plus lambda mu over t. This is step, unit step, you know. And okay, so this thing is like this. Now we are going to solve this thing. How it would be solved, we have, see, from here we can bring the, you know, we can take the value, we can bring the value for s, that would be s equals to minus lambda minus mu. So we are going to create a limit, that is s going from minus lambda minus mu, we bring the equation of s from here, the value or the values of formula from here, and this thing is we are taking our Laplace on this one, we are applying our inverse, Laplace inverse on this thing. So we bring it here, and we are going to multiply our this part s plus lambda plus mu to all the ones that are here, to every ones. This is the rule of our Laplace inverse, that we have to multiply with here also, and here also. So when we multiply here, it was, see, limit, first we create the limit, pws s of was this, so we bring it here and we multiply by the lower part, the denominator part, and it comes like here, a over s, and the same it multiplies here, plus b over s plus lambda plus mu, and it again multiplies here. So it multiplies with all the three parts. Okay, so what we got now, this thing cancels this thing, this thing cancels this thing. Now what it remains, and we are going to create our, you know, we are going to put our limit also. So it's written applying limit, by applying limit minus lambda minus mu plus mu. Okay, this is irritating as it is there. So you can see from here, this thing goes away, s plus mu over s. So in the place of s, we will got minus lambda minus mu plus mu. So this minus mu and plus mu goes away, so what remains, only minus lambda. As you can see here, this minus mu and plus mu goes away, and minus lambda remains. And what is the next thing, that is s. So s is minus lambda minus mu. So here it is, and you know, okay, what's next, it was equals to a over s, and this here also when we apply the limit minus lambda minus mu plus lambda plus mu, so these all terms goes away, and what remains only, that is A over S, and it would be multiplied. Obviously it would this term becomes 0, and when A over S would be multiplied, so this also becomes 0, so this is negligible. This is negligible, and plus B over, this thing goes away, this thing goes away, only B remains. So what it find out, what we see, this is A over S as we said before, and this thing that I told you plus B. So what it comes out, that B is equals to minus lambda over minus lambda minus mu. This we got this now. So we are getting towards our conclusion that we were going to find out B, and we have found it out. We have found it. So minus lambda minus mu, and this minus comes in common here, and lambda, obviously when it comes out it would become plus plus plus. Okay, and this cancels out. The value for B is this. So you know that how we can represent it now. We can represent in the form of like this. It's the rules for Laplace inverse and everything. That's another topic. If you don't know about Laplace or Laplace inverse, you can go in detail in the other videos of, or you can search it from anywhere. But being an engineer, you must be knowing about all these things. We have always studied about them from the very beginning. We are kept on studying them. Okay, so this thing comes in like this. Okay, now we are successful. You see, we are successful. We have removed all the S parts, all the S, and we are successful in bringing our system in the time domain. Okay, so here we are in the time domain. So Laplace inverse PW of S equals to, that is, we have found this. We were doing the inverse of the S1 in the S domain, so that's why it's written like this. And for A we got this, and for B we got this. Okay, now now we are talking about when PW is 0. So when we have at time 0, we are talking about at time 0. When we are talking about time 0, what we are going to get? Obviously when we bring this at time 0, time is 0, so this thing multiplies by 0, E0 is 1. So obviously E0 is 1. See, at time 0 E0 is 1, so this is 1 here, and this thing multiplies by 1, it comes here. So at time 0 we have this thing, and we solved both the things and we got 1. Proved. Oh, what is this? What we are going to say? We are going to say now, the at time 0, when we were at time 0, we have PW of 0 as equals to 1. So we are succeeded. As we say before, as we remember, we bring out, we consider our conditions, our initial conditions, and that PW of 0 is 1. We consider them now. So now we have proved it that it is obviously 1 by our methods and by our solutions and by our calculations also. So we have proved it that it is 1. So here our all the things and everything has gone to the conclusion, and they are all perfect. Everything is done perfect. That's why we have proved this as 1. We are having the proof of this as 1. Okay, that we considered before. Okay, so we wrote that when it is proved, so PW of t would be AW of t. Got it? So when we have proved that it is 1, so PW of t and AW is equals to AW of t. Now we would be talking about, remember what is availability? Steady state availability. As we know that the steady state availability at infinity, A infinity, is MTBF over MTBF plus MTTR. That is, I told you before in the start of this lecture. Okay, availability is something like this. So PW of t equals to AW of t. when we have proved it, so we can easily say that these both things are equal because we have proved it by our equations, by our solution, by our calculation. So we can easily say that they both are equal. So when they both are equal, so we can easily create it at time t infinity. Now we would be, first we talk about at time 0, now we would be talking about at time infinity, because we have to find out at a infinity, that is our steady state availability. So when we take it as time infinity, so pw of infinity, pw first it was 0 at time 0, now we are taking it as pw of infinity. When we take it as pw of infinity, what we got now, obviously okay, here you can see here, when e is minus, and when we will be taking it as infinity, t would be taken as infinity, so this whole thing would be gone to 0. Okay, this thing removes, it would become 0. Obviously exponent at the infinity is 0, everything would be, this multiplied by this, it would also be 0. So what it remains, only this part, only we have now this part at time infinity. So when we have only this part, so we can easily say that pw of infinity is equals to aw of infinity, as we said before that pw of t is equals to aw of t. So obviously the infinity would also be equal to infinity, and when we said this, now what we are going to do, we are going to keep these things as this, because we know that, I have wrote it before that mu is equals to if you remember, 1 over mttr, lambda equals to 1 over mtbf. Okay, so mu is the repair rate, it is equals to 1 over mttr. So we are bringing this formula, we are bringing this value in the form of a infinity, aw infinity, replacing it. Okay, so we know that mu and lambda, what are their values? Mu is 1 over mttr, lambda is 1 over mtbf, 1 over mttr and 1 over mtbf plus 1 over mttr. So this is simple multiplication, this remains here, and this LCM multiplication going on, you can see that mttr plus mtb, so you can I hope you can see that, you can see this mttr plus mtbf into mttr and 1 over mttr, and this thing goes there, they inverted, they can up and down, mtbf into mttr plus mtbf, and this mttr got cancelled out, and what it remains, mtbf over mttr plus mtbf. Here you can see this, mtbf over mttr plus mtbf. So it is proof, we have brought this a infinity in the form of like this, as we know that we already have the formula of a infinity as this, and we have proved it by our equation also, our calculation also. So the steady state availability of a single component, you remember the component, the a component that I the RBD that I draw before in the start, the single component, the a infinity of that single component of that single item would be in the form of like this. And that's all for this, that's all for now, the topic is over. We have done the a times infinity steady state availability at time infinity for the single component. Now in the next video I will be teaching what are the changes, or what are the scenarios when we have the two components in series, when we have two items in series. So what would be the challenges and what would be the solution for that. Okay, that's all for now.